Good afternoon, everyone. Welcome to the Network Seminar Series hosted by the Center for Network Intelligence at the ECE and RBCCPS IISc. It's my pleasure to introduce today's speaker, Dr. Harish Viswanathan, and he will be speaking on Future of Mobile, Extreme Connectivity, AI Native, and Beyond Communications. Dr. Harish Viswanathan is a head of Radio Systems Research Lab at Nokia Bell Labs. He received the BTech degree from the Department of Electrical Engineering, IIT Madras, and MS and PhD degrees from the School of Engineering, Cornell University. Since joining Bell Labs in October 1997, he has worked extensively on wireless research ranging from physical layer to network architecture and protocols including multiple antenna technology for cellular wireless networks, multi-hop relays, network optimization, network architecture, and IoT communications. He has published extensively over 150 publications. From 2007 to 2015, Harish was a corporative CTO organization where as a CTO partner, he advised the corporate CEO on technology strategy through in-depth analysis of emerging technology and market trends. He's a fellow of IEEE and a Bell Labs fellow. He received the 2023 Edison Patent Award from the R&D Council of New Jersey. Over to you, sir.
Okay, thank you very much for the kind introduction. I'm very happy to be here to talk to students and faculty from the Indian Institute of Science. Thanks for inviting me. And thanks to Satish for accompanying me here to make it easier for me to get here to the right place at the right time. Okay, so when I received the invitation, I had the option of talking about the broad overview of research we do in Bell Labs on wireless or a deep dive. And I noticed that a lot of the talks were deep dives, so when I asked, I got the response that a broad overview would be better. So I'm going with that, and perhaps next time I'm here, I can do a deeper dive. So what I'm going to talk about is what the future of mobile is going to look like, which is of course driven by the 6G design and specifications and implementations. And our view in a nutshell is it's going to be about extreme connectivity, which I'll describe what that means, AI native, and beyond communications. And throughout this talk, I will address these three themes. So before we dive into 6G, so I'm moving forward. Oh, now it's working. Okay, thanks. So first, a little bit about where we are in terms of 5G today, right? 5G has been deployed extensively. In fact, it was deployed faster than 4G in terms of the number of subscribers, adoption from the time of inception. And you can see a little bit of statistics from the different deployments in different countries, what the data rates that have been achieved are. This is coming from Ookla consulting company. And we get fairly good throughputs, really dependent on how much spectrum is available for the 5G network, right? So we've deployed mostly TDD for the high capacity, and massive MIMO has really been established to provide high data rates. So the technology that was developed, I'm happy to say, from MIMO and massive MIMO came out of our labs a long time back. And they have established that 5G is pretty advanced compared to the previous generation. And in terms of monetization, it's mainly about subscription conversion, which means a lot of the plans have become all-you-can-eat data for a higher price. So that's how the operators are making more revenue from 5G. And fixed wireless access has come up as a new use case that was not there before, which is surprising, mainly in the US and some other parts of the world. And the last one is some use of 5G for new services like gaming, AR, and things like that. Okay, so when we go to, yep, sure.
UK and Japan are doing pretty poorly, I mean, compared to the rest of the world. Yeah. And you mentioned this is because of spectrum allocation. But why wouldn't they want to allot more spectrum for 5G?
I think they're just slower. Like Japan, for example, has not deployed massive MIMO. Japan still went with more traditional 4T, 4R, and reason we get is, for them to find the sites, massive MIMO sites is harder. They are typically don't want to co-locate the base station with the antenna on the same site. So it's, the way the infrastructure is in Japan, they rely heavily on the remote radio heads. And that kind of an architecture that is not very suitable for massive MIMO. So now they're okay, so what is the vision for the future? So I think in the future, humans will not only inhabit physical worlds, but also digital worlds, which are high resolution, spatially accurate, real-time representations of the physical world through a lot of sensors, etc. And the goal and the real-time communications would be about making the experience in the physical and the digital worlds seamless. And digital worlds will enhance human intelligence because you can play back and fast forward. And what we are talking about is extension of the digital twins of today. Like a lot of factories, for example, have machines and digital twins of them. They run simulations, predictions, etc. And imagine extending that to the entire factory or a smart city. So you have representations of all of that. And then we would control the real world through these digital twins. And the human world is basically a representation of the human in the digital twin as well, including our physiological parameters, maybe even our moods and things like that. And the human augmentation refers to the augmentation of the human intelligence that comes from this ability to fast forward and feed or play back, as well as through other sensors and actuators that we can attach ourselves to. So in terms of the use cases, we believe there are 3 classes of use cases. And now we're talking about, not just 2030, but in the whole space from 2030 to 2040, which is the future for 6G, let's say. So immersive experiences driven by this augmented reality. Maybe some people even talk about holographic telepresence and things like that. Augmented intelligence, as it is, we have a lot of AI agents. So the network would be about communication of intelligence and having digital assistants. Those kinds of new applications are likely to emerge. And then the last one is seamless control, which is, as I said, about being able to control the physical world through the digital world. And we have already, even here I saw Art Park, things like that, where you want to control a robot from a cloud AI application. So you need networks to enable these sorts of things. Okay, so just to give you a bit more insight into that, here are some statistics from some consultants on how fast things are growing. The smart glass shipments are growing pretty exponentially, or expected to grow pretty fast. And companies like Meta have really interesting glasses. And there are good applications of that. Of course, not everybody is going to wear these glasses all the time. But if you are a tourist, or if you're sometimes even, say, doing grocery shopping and you want to show what you're seeing to your wife, I think is really good. Some use cases like that are emerging. And then going further, humanoid robots could also be pretty interesting. And a lot of companies are working on these kinds of or devices and applications. And there may be also things like AI-powered handsets, and then extended reality glasses, which are starting to appear that I talked about. So I think one of the reasons to evolve into the future, new generations, is having these types of devices, new devices. And then, yes. Yeah, like you restrict phone usage, you may have to restrict glass usage, or at least inspect their glasses before they enter the exam hall. Yeah. Yeah. You have to leave everything outside. Yes. Okay, and the AI is another big transformation that's happening, which will certainly have an impact on the networks. So we have these devices that maybe highly capable of running AI applications, but still to tap into these very large language models, we're talking about hundreds of billions of parameters, probably won't run on the AI powered device simply because of the power consumption. We know how much power it takes. So you would still rely on offloading, and that means there's going to be an impact on the network that we need to design for. And here's an example of some of the use cases that are already there on 5G with AI on the various devices like Apple and Samsung. And one observation is that there's likely to be an increase in the uplink traffic from this, right? So you can see some of these applications are high on the uplink usage. And so the proportion of downlink to uplink traffic could tilt a bit towards more uplink. And so future networks would have to enhance the uplink. Another reason to rethink, how we do the network. So some other technology evolution that's driving the mobile network evolution here. So we talked about the AI, but from an application point of view. And here I'm making a statement about AI from a use of AI for the networks point of view. So we have a new tool, and what can it do for networks, right? So I think that's something we have to really explore. And we expect that this to form an important part of the future mobile network. As always, compute is constantly advancing. We deployed 5G with 7 nanometer node technology, and now we are evolving to 3 and then maybe 1 nanometer. And then there's further evolution like new architectures, GPU type compute or compute in memory. And we want to make use of all this to reduce the cost per bit. Every generation has reduced the cost per bit from the previous generation by a factor of 10. And that's what's allowing us to, pay the same and still enjoy a much higher capacity applications, etc. And we want to continue this trend. Another technology is quantum security. So quantum computers are not there yet, but maybe in this time frame of 2030 to 2040, we can see quantum computers. And so we need to make our networks already quantum safe. And this requires new schemes to be standardized and deployed in the next generation. Then we have the whole network cloud continuum as an emerging technology. So being able to move workloads between the core data centers, edge clouds, devices, and then how do we handle all that in a mobile network? As you move, if your application is running in different parts of the cloud infrastructure, handling that mobility, etc., is an interesting new technology problem. And then the space communications is something that will again change how we design our network. So incorporating the non-terrestrial networks into mobile networks is definitely happening, and that again calls for enhancements to create direct to cellular communications. So this is another reason to think about a new generation. And then the last one is sustainable technology. So energy efficiency is becoming much more important in the current world. And so, we need to pay attention to that as we design our new generation. So in summary, I think the use cases evolution and the technology evolution form the basis for why we need a new generation. This is a question that's often asked, and these are some of the answers. Okay, so now I'm going to dive into my 3 themes and where we really hit on the technology research that we are doing. So the first one is extreme connectivity. So the basis for that, so before that, what do we need in terms of extreme? Why is it extreme connectivity? So I use that term basically to mean that we want 10x better capacity, better coverage, especially when you go to these higher frequencies, which is just the mid-band frequencies from the 7 to 8 gigahertz, let's say. You do want better coverage so that you can use the same site grid. So we need to achieve that. And then we want to achieve 10x better energy consumption per gigabyte, right? Or at least 2x better average energy consumption, because the number of gigabytes is going to go up by 10x. So this doesn't really reduce energy consumption. But average energy should go down on top of this 10x per gigabyte. And then the last one is operational efficiency of the network when you provide this connectivity. So this is basically what I mean by extreme connectivity. And the question is, what does it take to achieve all this? So first thing that it takes is spectrum. So every generation has relied on new spectrum. I mean, that's the motivation to deploy new radios. And so here again, we expect that we will achieve eventually a substantial amount of spectrum for the new generation. You know, it varies by country, what type of spectrum and how much of the spectrum is available. Yeah. Yeah, so that's definitely a focus of that. Yes. Right. At a certain cell site, from the cell site's perspective, we are extending the range at which you can achieve the same data rate, let's say.
But there's also the deployment aspect, how you deploy the network and how that affects the coverage.
Yeah, that's right. So this is without densifying. So when we say this, we want to achieve this without densification. So yes, so this is the spectrum picture that it looks what it looks like in different countries. But the bottom line is we are looking at least at a 200 megahertz carrier for an operator, for say three operators in a country, sometimes even more. And India is in a very good position. I think it's one of these peaks here that we have. Yeah, in the Asia Pacific, you have close to 1200 megahertz of spectrum in the upper 6 gigahertz and the lower 7 gigahertz. And still a lot of work left to be done to realize this. But once we realize that, then we have to exploit this spectrum. So as I said, it can be 300 to 400 megahertz per operator that we are able to achieve. So if you have this spectrum, then what do we do with it, right? So first approach, or really the only approach to get these sort of big 10x type capacity increases is through the expanded spectrum and through expanded antenna arrays. Okay, so here, if you go from 5G at 3.5 to 6G at say 6 to 8 gigahertz, basically you are doubling the frequency, or basically half the size of wavelength. And so for the same array dimensions, which are typically limited by what you can put on the tower, what you can put on top of the building, you know, there are restrictions on how big the array size can be. So the point is that for the same array size, you can have many more antenna elements, because now the wavelength is smaller, you can space them much more close by, right? So this is really what we are thinking would give us the increase in spectral efficiency, because now you can do more layers with the larger number of antenna elements. And of course, the array gain goes up in terms of the frequency difference, but it just compensates for the higher loss at the higher frequency. Okay, so the challenge is to reuse the existing base station sites, even though you're doubling the frequency, which means that you have to achieve the same coverage, or actually the goal would be to get even better coverage at these frequencies. And then get a cell capacity of 10x, which would be a combination of increase in spectral efficiency and wider bandwidths. Okay, so 4x more bandwidth and 3x more spectral efficiency, or something like that, to get to this 10x capacity. But it doesn't happen without innovation. So of course, the first one here is referring to above the horizon power limits, because you're now sharing the spectrum in this band with satellites. So already in the World Radio Conference 2023, they imposed a restriction for the upper 6 gigahertz on how much you can transmit above the horizon, right? So then we have to design our antenna arrays and beamforming solutions to tackle that while we deal with this coverage problem as well. You know, terrestrial coverage, but the side lobes have to be restricted. Then we need hybrid beamforming perhaps, because we can't have all digital with so many antenna elements. So somehow we have to do that. And then new things like, crest factor reduction, which is basically how we shape the signal. You can think of it as a waveform modification. So even though you have OFDM, we do clipping and filtering and digital pre-distortion so that you can make a better efficiency out of the power amplifier. But you can play with it spatially as well. So normally we put the distortion in frequency domain. When you clip, you're going to create a distortion, and then you're filtering so that the distortion is managed in the sense that it doesn't create degradation in the EVM, error vector magnitude. So instead now another angle to that is to say, okay, I can allow for higher EVM because my distortion is only in certain directions, not in the direction where the receiver is. So that's a new concept that we are working on. And then of course the modular architecture that I'm going to talk about. So given the limited time, I will just touch on some of the research a little bit, and if you have questions, we can discuss a little bit. The satellite receivers. Yeah. Okay, so here is a bit of insight into the research. So I show a picture of the radio unit that we have. So typically you have the antenna, some PAs and LNAs, beamforming ICs, and the RF sock, which is basically digitally up converting to the RF frequency and then converting it, the A to D and D to A are in the typically integrated into the RF sock. And then we have the L1 low processing, which is the lower layer of the signal processing that's required for MIMO, things like IRC receiver or MMSC receivers that you may be familiar with. So in each of these areas, we have research that's going on. So the first one is what we call meta-surface beamforming. I know the academy has worked a lot on reconfigurable intelligent surfaces. I mean, it's an interesting concept, but it's very difficult to implement in practice. You need to find a site, power. Even though it's low power, there's no way it can work without plugging it into the grid. And so operators generally don't like, trying to find new sites and things like that. So RIS is fine, but it's not really useful. What we've done with that or with similar technology is to use it right at the base station itself. So you can use this to shape the signal that's sent by the antenna by controlling the meta surface. It is based on metamaterials whose dielectric can be adjusted based on a control signal. And so we can create vertical beamforming. So we don't use it for horizontal beamforming. So you would have horizontal beamforming done digitally and the vertical beamforming done through this meta surface. And the reason to do that is because it's more energy efficient than using phase shifters in the radio. Phase shifters are lossy. They have insertion loss and other losses. So the net benefit would be that you save 1 or 2 dB in terms of energy consumption, basically. The second big thing that's happening, and which may or may not see the light of the day, to be honest, is the subband full duplex. So full duplex is transmitting and receiving within the same spectrum in time division duplex, right? So in time division duplex, you normally transmit during certain time and then you receive during certain time. But what we are trying to achieve here is to transmit and receive simultaneously by doing interference cancellation, because there will be a lot of leakage from the transmit side to the receive side. So you have to suppress that interference if you're going to be able to hear another device, right? And so subband simply refers to you're not using exactly the same set of physical resource blocks to transmit and receive, but adjacent resource blocks. So there is still a lot of leakage. So the question is, can we actually achieve sufficient cancellation, isolation to transmit at high power? The whole challenge is to do it for macros, right? It's easy to do it if your transmit power is small, because then the leakage power is also small, and with the current UE powers, you can overpower the leakage. But if you are talking about very high base station transmit powers, then you need very good isolation and cancellation to achieve that. And here is an example of some concepts that we have developed for this at the antenna array. So we have now a transmit array and a receive array. with some kind of a material here. So this is a new concept to have this electronic band gap with partially reflecting surface that shows that you have a very active transmitted signal, but on the receive side is very low power leakage, right? So this gives us close to 80 to 85 dB isolation while not increasing the dimensions of the array too much. You don't have to separate the transmit array and the receive array far away from each other because of this new material that we can insert into this. So that's a technology for the subband full duplex. Of course, hybrid beamforming basically refers to the fact that you could have a combination of digital and analog beamforming, and this comes with a host of problems. To start with, how do you learn the channel to do this kind of beamforming, and how to do the scheduling? Do you try to isolate users in the analog beam or only digital beam? Things like that. I already talked about the spatial signal shaping, which is the the spatial crest factor reduction, and then I'm going to talk about the receiver algorithms next. So this is an important area for okay. So basically the top, let's start with the bottom actually. The bottom shows how you can build a textbook like receiver, right? So if you have a large array, okay, you take all of the digital signals from the whole array and then do a MMSE detector, classic textbook stuff, right? This is how you would do it. And then, yeah, so this is the interference suppression. The other cell, okay, so it's a little bit more complex. That's the other cell interference, and then within the cell equalization. But this tends to be too complex to implement in most hardware implementations because you're talking about very large arrays. So then what you do is basically do dimension reduction by going through the antenna domain to the beam domain. So you initially take a subset of these elements and do some fixed beamforming, long-term beamforming based on the covariance of the channel, and then do the IRC or MMSE processing on the subspace, basically. So you would go from something like 128 TRX to just 16 or 64, and then do a MMSE receiver on that, right? And these are slowly adapted based on the covariance of the channel. We come up with another concept here, what we call the sub-panel receiver, which is more modular in the sense that, okay, it's trying to mimic this one, but by splitting the antenna into multiple sub-panels and then running a full interference rejection combining, which is similar to the MMSE receiver for the whole sub-panel, and then doing a joint processing across these sub-panels. So each of these has visibility only to a portion of the array. And the advantage of that is it's modular, so it's much easier to implement. The interconnectivity between the digital front end and this receive processing is a lot simpler. You don't have to have a mesh connection that connects all of the array elements to all of the ASICs that are doing this, because you're running a separate ASIC for each of these things. So anyway, so that's some new ideas on how to build a receiver for this extreme MIMO. So people always ask, what is the research in going from massive MIMO to extreme MIMO? And these are some of the examples of the research that we do. So here's some results that you can see here. So it shows the 3 types of architectures for the receiver that I talked about. The full array, which obviously does best in terms of the good put or the spectral efficiency, but then it has much higher computation, the red ones, right? This is for 64 TRX, 128 TRX, and 256 TRX. Whereas the receiver, we come up with the modular architecture, basically called the sub-panel, provides about half the gain with almost no increase in complexity, because we broke down the full array into sub-panels and did the processing like that. So anyway, so that's has some clear advantages, and we are making a push for implementing the products in this fashion. Yeah, so above the horizon, I already said what the issue is. So basically, you want to suppress the side lobes, but you can't just tilt the antenna down because you want to increase your coverage. So we use new techniques to do this. If you do the traditional filter-based design for the beamforming. So here it's talking about the fixed beamforming of that, not the digital beamforming, but the fixed vertical beamforming that you design into the array, right? So you can do it like a filter design, like a Chebyshev filter or whatever, to suppress the out of band emissions. Here in this case, emissions in the directions that are undesired. But the problem with that is it doesn't take into account the distribution of users, which is then the precoders in your cell. So, for example, you could have a high rise in your cell, and how do you deal with that, right? So you cannot like just down tilt the antenna. So we say, okay, we can do a cell site specific data aided design. So you take all the different channels that the cell site might see, depending on the user distribution, and then try to come up with the sort of a loss function that takes both the KPIs into account, right? So you have one that says, okay, how much do I have in terms of the out of band emissions, and also how much do I see in terms of the SNR of the users within the cell. So those are the two, and you want to try to maximize one while keeping the other one small. So then you can create this kind of a loss function and run a stochastic gradient descent to determine the beam weights. So this would be a much better approach, turns out, than any of the filter design approaches, because this really can maintain the coverage while minimizing the out-of-band emissions. Okay, so now I'm going to switch to energy efficiency, which is another aspect of extreme connectivity. Yeah. 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 That's right. It's like a sector beam, yeah. And the digital beamforming is within that. Yeah. This is fixed. Yes. Right. Okay, so energy use in mobile networks. So this shows where the energy is going. So 73% is RAN, basically, right? This all aspects of energy are taken into account: core network, RAN, operations, data centers, and of course here we're talking about data centers of telcos. And 73% is RAN, and within that, 29% is the radio. Okay, so that is the biggest source of energy consumption. So we are focusing, and within that, the power amplifier is of course the largest one, 17%, and then the DFE and converters. Converters means A to D and D to A, basically, and DFE is digital front end. These are the two that consume the most. What is going on here? The digital front end is processing intensive because it's doing the digital pre-distortion, the crest factor reduction, and the FFT. So these kinds of things is being done here. So we focus our energies on how to reduce the energy of this portion of the energy consumption. Okay. Now this BTS air conditioning and stuff, it comes mostly from 2G and 3G. So if you're really focusing on just the 5G and 6G, it's going to be even more radio intensive, because we don't need any more cooling and things like that for the baseband. Technology has evolved, and then fans and liquid cooling and things like that are good enough. So we won't need. This is like if you have a cabinet and you have to have an air-cooled cabinet, and so, because this picture itself is a mix of 2G, 3G, and 4G. Okay. So another interesting observation is, if you look at the 4G versus 5G, okay, so what do I have here? You have capacity or load. You can think of this as load, and this as the power consumption. So you can see 5G is actually 20x more capacity possibility than 4G. So we are now allowing for higher 100 megahertz, MIMO, all that is incorporated here. So here we are talking about 10 megahertz LTE. So its power consumption versus load looks something like this, and this is 5Gs, right? And I'll explain the slope here in a minute where we get this. But the point is that at zero load, you still have a significant amount of power consumption, and 5G's zero load power consumption is even more than 4G. Okay, and then now in the 6G, the next iteration, we have another 20x or 10x to 10x is more like it. And so it's going to increase the peak power consumption by a factor of 2, we think. But the point is we want to keep the average much lower. So when you go below the 5G type of capacities in terms of load, we should do much better than 5G. Okay, so this is kind of our goal. So what is the slope, right? And that's what is there in the next slide. So there's a whole bunch of techniques to adopt. Some of it is already in 5G, but some will be coming up in the future to make the energy consumption of the radio unit scale with the load. To start with, it has energy consumption for the power amplifier, as I said, the digital front end and baseband, and sorry, this is the baseband and this is the digital front end. So this slope is coming because you can turn off the PA when there is no load, meaning if there are no packets to send, you can reduce energy by just turning it off. But you can only turn off some parts of the base station, and that explains this big leftover energy consumption. So this is the state of the art today. It's called micro slots or micro DTX, right? You're going down to the granularity of a couple of symbols to cut down the energy consumption. The next step here is to realize that, okay, this is not really optimal because, we know that Shannon tells us that the spectral efficiency is logarithmic in terms of the power. So if you're willing to give up a little bit of spectral efficiency, you should see an exponential reduction in power consumption. So that's what we want to achieve when we go to the next step, right? And this can be done with proper power management coupled with the drain voltage modulation of the PA, because part of it is the PA efficiency. As you back off the transmit power, the PA efficiency goes down. So you have to adjust the PA's drain voltage so that you can maintain that. The next step is MIMO muting after that, right? So you have a large array, but if you have no traffic, why do you need a large array? So you have to do a MIMO muting, but still try to maintain the coverage. So we will try to keep the array aperture the same, and by selecting these antennas that are not close to each other but far away from each other, right? Keep the array aperture the same, but mute a lot of the transceivers. So that allows us to go down in the step fashion. And then we have to achieve the same sort of scalability on the processing. There's all these techniques for the SoC power islands. So you can turn off portions of the SoC, or the SoC is made of chiplets. Then you can turn off some of the chiplets and keep only some of them on. So then you get this step function in the chiplet power consumption. And then last is also, of course, trying to reduce the peak power itself with a better PA technology, right? So all of this goes into trying to make the energy efficiency better as we go into the future. So one concept that we worked on especially is to realize that the conventional approach to doing the pre-coding is not really optimal from an energy point of view. So you might be doing zero forcing, eigen zero forcing or something like that to do the MU MIMO, right, on the transmit side. But it has a very poor power profile. So this is the power profile across the different PAs. So you have like 768 PAs in your array, and your power profile looks like that. And this is the PA saturation power, and you have to back off from the saturation power based on the peak power of one of the PAs. And the remaining PAs are much more backed off compared to the saturation power, which is totally unnecessary to back off so much. And this makes the pre-coding pretty poor from an energy efficiency point of view. So we come up with an idea called flat pre-coding, where you try to balance the power across all the PAs. So this is, taking additional constraints in your pre-coder design. So it won't be anymore just the traditional zero forcing based on a sum power constraint. That's what you have on the left. Whereas here you got to have per antenna power constraints to do that. And that turns out to be a slightly different optimization problem. And then now you can say, okay, the back off you impose is the same for all the PAs. And so your energy efficiency is going to be pretty good, right? Yes, of course you want to make sure that you have the same performance, which brings me to the next slide. So you say, okay, my optimization is going to be maximize the weighted rate sum subject to, the total upper upper bounds on the radiated power, upper bounds on each panel power, and now the new thing is also incorporate lower bounds on the panel power. Okay, so that's the trick here, to impose a lower bound on the panel power. So if you just impose upper bounds, which is what you need anyway, per antenna power constraint is important in a practical system, you'll get a profile like that. And by imposing a lower bound, we get this. Now with this maximization of the weighted rate sum, and you can look it up in this publication, we can actually achieve almost the same efficiency. Of course, there's a bit of a loss, but it's almost the same. And then the techniques are given here. I don't want to go into the details. Some things that these guys came up with, it's not my invention here, but there's a way to solve this optimization problem for both the zero forcing and the weighted mean square error.
Because the power amplifiers are not identical, right?
No, they are identical, but our precoder is not using all of them identically. It's using some of them efficiently and some of them very inefficiently, because it's not same power across all the TRXs.
So, why not know that many of them, here you have a uniform backoff for all,
Yeah.
then there is a distribution.
Yeah.
Then some of them hit the peak and have distortion. So, that would say that you can avoid the backoff
Yeah.
and operate there.
Right.
There's only a few that are essentially suffering the distortion
Yeah.
due to the power. So, what about that approach? Why have a backoff at all when you know that most of them are not going to come to that point?
No, I mean, you have to still meet the error vector magnitude. The distorted signal is not acceptable for the UEs, right? So you have to make sure that the whole chain is linear. You can't have non-linearities in the chain.
The configuration of the antennas for various signals that actually have these powers, I presume that you don't have control over that.
That's right. We don't know which antenna is going to be here and which one is going to be there. And that's dynamic because it depends on the channel, right? So there's no way to say, okay, I'm going to operate this at this power back off and this PA at this back off. That won't be a solution because it's going to change over time. Yeah, I didn't bring the plots for the spectral efficiency, but yeah, you can take my word that we don't lose much in terms of spectral efficiency.
Many years ago, there was this idea of geometric mean decomposition. Instead of using an STD type approach, we choose decoding vectors. And what that does is to actually try to address something like this, to have
Okay.
power across
I see.
antennas. Maybe it's
Okay. Maybe it's related, yeah. All right, now I want to go to my next section on AI native. So what do we really mean by AI native, right? We use this term a lot. So I think, I thought I'll explain that a bit, at least from my perspective. So the first one is what I call basic, which means, okay, you use the tools in the process of the design and standardization. It's completely offline. For example, you use the tools to read the specs or summarize the specs, something like that, right? Find the errors in the specs, whatever. So this is one version of using AI ML in our design. The second one is substantial number of system capabilities rely on ML. So now we are now talking about doing a receiver with ML or some inference in real time with ML. So then it starts to become, okay, quite critical for the functioning of the system. But then there are other aspects. It needs something called a framework to make the number two a reality, because it's not a one-time thing to deploy a model and just leave it, because there's going to be retraining, you have to do data acquisition, push new models into the network and into the device. So all of that requires a well-functioning, what we call an AI/ML framework, and that needs to be standardized so that it can interoperate between the device, the network, other networks from other vendors. And then the last one is something to do with compute. And okay, you could argue that this doesn't have to be the case, but accelerated compute is definitely needed. The programmability is good because then you can more easily change your model architecture, evolve faster. So that would be the other thing that we want to incorporate. So I think all of this will become a part of reality pretty soon, in my opinion, probably in the 6G time frame. And that's how networks are transforming going into the future. So we do research on all of the layers. So we believe that there's a role for AI across the layers. Of course, the impact really depends on what you're doing. It's not, the benefits are not the same. But at layer 1, we have what we call deep TX and deep RX. I think I'll talk about it in the next slide, so I won't touch on that. But and then the higher layers will be mobility, beam management, radio resource management, and things like that, where we can, radio resource management is basically the scheduler, so which is a very complex piece of code which we want to try and do with this. And then we have core network and applications. Everywhere you can use it. Intent-based network management is a very important use case for AI in networks. How do you automate networks, right? So network automation is a critical piece. And as I was saying, all these 4 things have to come together for this vision to become reality, right? So you need use cases like these which show benefits. You need a framework, hardware acceleration, and also standards. So that's what we are driving towards for the future. So let me touch on one piece of research that we've done. We call this Deep RX, and many people call this neural receivers. We were among the first to come up with this, but it's now being replicated by many different companies. The idea is to take the receive functions and see if we can fuse some of them to jointly optimize them. Okay, so if you jointly optimize the channel estimation, equalization, demapping, etc., that's basically what we've been calling Deep RX. It's based on a convolutional neural network, like a ResNet-like architecture. And the main advantage of this is really data-aided channel estimation. We always had iterative channel estimation to improve performance, right? So you could do first round, do some level of demodulation and decoding, then use that to improve your channel estimates, because now you have all these symbols that you kind of know what they are. So then that means you can use them to improve your channel estimates and do this. And that's the clear benefit from doing that. Papers have been published about that a long time ago. But the cool part is, this is basically doing that. And some people do it as deep unfolding. I think you worked on that. Essentially, that's what this is doing. So without realizing it, I mean explicitly stating it, this Deep RX is basically doing an iterative version of that channel estimation. So, and that's the basis for also saying that we can significantly reduce the amount of pilots that are needed at various speeds. And that's where the majority of the gain comes from. So here is an example of the results that we have on this. So you have Doppler shift and uncoded BER and coded BER here. And the comparisons are between, how many pilots you use and, whether it's LMMSE or Deep RX, right? And this is for four layers, and that means 4 simultaneous streams on the uplink receiver. And you can clearly see that if you have very little pilot, you're going to do worse and worse. Whereas the deep version maintains its performance close to the known channel at any speed for the same amount of pilots. And you can get similar comparisons in the case of coded results. And this has now become quite an important use case in 3GPP discussions for 6G. And there are various versions of this, reducing the amount of DMRS or constellation shaping, etc. Another use case that we worked on is what is called hybrid Deep RX. Here on the uplink, we are trying to allow distorted signals. So the goal is, okay, so this is showing the PA output versus amplitude. This is the typical PA curve. And you can see the saturation at the top, right? But what if you're able to, so normally we back off and operate here, but what if you're able to operate here and still do pretty good detection of the symbols, right? The signal will be nonlinearly distorted, basically. So by doing higher power transmissions, you can get better coverage or throughput, or also power efficiency because you're backing off less the UEPA. So we worked with Rode and Schwartz here, the messy setup in our lab, to basically show that digital post-distortion compensation is possible. and it means that we can achieve 2 dB lower back off, essentially achieving these benefits. Yeah. Yeah. This is what I said. LMMSE is just doing the channel estimation with the pilots alone, which is just one symbol out of the 14 symbols or 2 symbols out of the 14 symbols. But whereas the deep version is using all of the symbols to do the channel estimation, which you can do with iterations, right? It's very difficult to implement the iterative version because the processing is not homogeneous. You have to pipeline that feedback, and you need to know, which one is noisy, which one is not noisy. Whereas, oh, sorry, yeah, I said data aided, meaning the transmitted data. But of course, training is needed. Data is needed for training as well, and there's a whole story behind that. Synthetic data versus field data, how much you have to customize site specific. Yes. Yes. So here, it's just that, okay, our intuition is just that you are introducing nonlinear processing in the receiver to somehow deal with the nonlinear distortion. It's not exactly clear beyond that why it works, but okay. Yeah.
You could say that, okay, I'm going to use the data bits as well. Of course, iterative is one.
Yes.
So maybe think of a time-one way of making a soft decision on data and using it as a
Oh, without decoding, you're saying?
without decoding. Yeah. So
yeah, we played with all that. Yes, I mean we are constantly challenging ourselves, trying to do all these kinds of things. Some it'll do it also to a certain extent. Oh yeah, no, but mobile costs. The mobile guys like Qualcomm, they want to do all this to make their mobile differentiated, right? Their challenge is, okay, I can make my mobile better if I get 2 dB better coverage. So let me do everything I can in my Snapdragon chip. So the industry is happy to do that. More processing is differentiation for Qualcomm. All right, another version of the work, actually joint work with Qualcomm, is interoperability for what is called CSI compression. So everybody knows what CSI is. Basically, you are feeding back from the UE to the transmitter the estimates of the channels for doing the downlink pre-coding on the base station. To do that, you can do traditional methods like what's standardized in 3GPP, right? So get the eigenvectors and send quantized versions of the eigenvectors, etc. So there's already some level of compression. But the realization is you can treat the channel estimates of the UE as like a image and do image compression methods to do even better compression. But when you do that, the encoder is coming from the UE vendor and the decoder is coming from the base station vendor. And typically, these compression schemes are designed as an autoencoder, where you have to train jointly the encoder and the decoder. And now we enter into a business problem that nobody wants to reveal their model. So Qualcomm doesn't want to reveal their model in the standards, and we don't want to reveal our models, etc. So the challenge was to say, okay, can we independently train these and still make this thing work? So that's the new part here. It's called sequential learning. And it's very simple. The basic idea is one party, and I'll use the example of the device vendor, they train the encoder and the decoder together and share with us basically the input and output of the encoder alone as training data. So, and then we use this as the training data set to just train the decoder alone, right? So then we have no idea what architecture they've used, but still are able to design a decoder for that encoder. Basically, that's the idea. Of course, we also have to agree on what this QI means here. Of course, that's part of the standards. But beyond that, all we need is the training data set, and this is how we establish that you can have interoperability without revealing any models. No, it's in the process of being standardized. Yeah.
But the data set should have all the VIs that you'll see in practice.
Yeah. So always that's actually the next slide here. So how robust is this, right? Like how often do you have to retrain? And also there are questions about, okay, there are multiple UE vendors, multiple base station vendors. We have to deal with all these problems. And so we try to say, okay, can we make it robust enough, or is there really a benefit from doing site specific? So in our facility, this is the Murray Hill facility, where the home of Bell Labs for, I don't know, 75 years. We are still there, and we have our own base station set up here, all built by our Bell Labs research team, with UEs from Qualcomm on these cars. And we did this experiment, basically. So, and then we, of course, also did it indoors, right? So 2 different environments, actually 3 different environments. 1 is outdoor and 2 indoor environments, open office and some other type of cafeteria, all these kinds of things. And so the question is, how does a common model work compared to an adapted common model? That's one question, right? So common model means I put all the data together and train and get one model, or I train site specific. And this actually showed that the performance, I mean, this is throughput performance on the downlink, because that's what ultimately matters. The throughput performance is basically the same whether you use a common model or an adapted common model. We also have results showing that if your data set is not very broad, meaning if you train only using outdoor data, it fails indoors, and vice versa. If you use only indoor data, actually, if you train with indoor data only, it actually works reasonably well outdoor, because the indoor channel is much more complex. But the message here is, if you have a very good training data set that's a mix of a lot of different channels and environments, you can get a pretty robust model. So this is good news in some sense. But some people look at it and say, okay, I always thought that AI is about being site specific, and you're saying that you don't need to be site specific. I think this is probably true only in the lower layers, where you're not exploiting human behavior. I mean, it's not about user distribution, but more about electromagnetics and channel and things like that. So we can make a broad enough training set to make it work. And here it just shows the gain in throughput relative to the type 1 CSF. So it's at different locations, indoor and outdoor, we get substantial benefit relative to the current approach of doing type 1. And with type 2, which is also standardized in 3GPP, the main benefit is compression, not the throughput gain, because type 2 sends a lot of data back to the base station. All right, I have no time to talk about this. Either I could just stop here and say my talk is over, or I can talk a little bit about this. I don't know what people think. 2 more minutes is fine. Okay, so beyond communications is basically about sensing. So we are realizing that as we evolve, our networks are reasonably dense already with 5G. The site grid is dense. We have very wide bandwidths going even wider, and we have MIMO. So all of these are ingredients that are needed for radar capabilities, right? So why not turn the base station into a radar? So that's basically what this means. And what is the idea behind this is looking for use cases beyond communications. So expand cellular service capabilities for objects that are not connected to the network. Of course, if it's already connected to the network, we can localize the objects, right? Here it's passive objects that are not connected, like a drone that's a rogue drone or something like that. And then we want to, the advantages are, of course, we are reusing the spectrum compared to mounting another radar right next to it. And radars are not that cheap and don't work in sort of short range distances, because the FMCW radars have a blind spot and they cannot be used for detecting things that are short range. Okay, so this should lead to new monetization for operators. So basically, these are some of the potential realistic use cases for base station based sensing. The drone one is the most important one from a commercial point of view. We have significant interest from public safety, prisons, government organizations, military, interested in this drone detection and intrusion detection. That's perimeter safety sort of thing. Of course, it can be used for roadway and rail track monitoring and things like that. And indoor is, if indoor base stations are deployed, then for factory automation. The most important use case here is safety. So if somebody is going too close to a big robot geo-fenced area, then it can raise a flag. Okay, and these are some of the requirements that we have to achieve. So let me just cut the story short a little bit and say that we have done a lot of research and experiments here. So this is millimeter wave based experiments that we did in our Stuttgart facility. We have a transmit and a receive. Eventually they'll become full duplex for sensing, right? Because it's too expensive to have two radios. But for experiments, that's what we're doing. And we send signals, and there's a drone there. We capture the reflections and do a lot of processing. The raw periodogram or range speed plots, right? They look like this because there's a whole bunch of scattering happening from various other things. And then you have to do a lot of signal processing to do clutter removal to get to the target. So we have this thing up and running to demonstrate that we can detect drones up to 300, 400 meters in millimeter wave, and hopefully even more if it's FR1. And there are various other versions of this, like looking at bistatic and passive sensing. There's a lot of research that's going on in this space. Okay, so then let me skip this one. Just to conclude, 3GPP is already, of course, very active 6G standards. We have had the first RAN workshop earlier this year, and now also multiple RAN 1 meetings, etc. And the target is to get the standards ready by the end of 2028. And we should see first 6G products by 2030. Okay, so that's kind of the timeline we're looking at. And with that, I'll just conclude by saying that, you know, the future is about three things: extreme connectivity, AI native, and applications of the RAN on communications. Okay, and we have working on the technologies that will shape the future for at least the next decade. Thank you very much.
Thank you very much, Professor, for giving an interesting talk. Are there any more questions from the audience?
Yeah, I glossed over it a bit because of time. But yes, it's an important topic for sure. I think the new research there is, you know, GNSS free positioning. Like, how can you just do positioning with just the LEO satellites? Also, better interoperability between terrestrial and satellite networks, right? So, spectrum sharing is required if you're doing direct to device in the same area. So, I think those are some of the important topics. We also worked on the same we call it flat beam synthesis. There you're not doing pre-coding from the satellite, but you're still forming beams. And the current technology is all about like doing Chebyshev filters as beam vectors. So we said, okay, why not apply our flat beam concept to the satellite problem as well, so you can make more efficient satellites. So things like that are happening.
What about future working of Wi-Fi and cellular?
It's not going to happen. We did that in 4G. It didn't take off. No one has an appetite to do anything like that again, except in the core network, right? So, of course, all the operators have already deployed some version of this non-trusted networks access to 3GPP, right? So, you can have Wi-Fi traffic routed back to the mobile core network. That exists, and you can do Wi-Fi calling from your home. It will go through your operator network, and then, a voice over IP call, things like that. I don't think at the lower layers there's going to be any integration.
Yeah, thank you for nice talk. So I have two questions. What is your take on cell-free system for 6G is for future mobile connectivity? Is there any
I think that's another topic we did a lot of research on. I think it's very difficult to implement in practice. You know, the problem is that you have to front haul all the IQ samples practically to do joint processing somewhere. You know, Cloud RAN has never taken off as much as we thought it would. Front haul is still pretty expensive. And then also some difficulties with doing the synchronization across these different radios. So I think the cell-free will always be a niche deployment. So we do some level of uplink cell-free, or in my case, basically distributed MIMO, let's say, for stadiums, right? You have very heavy traffic, you have lots of smaller cells, and the RAN is basically at the site, so you can collect IQ samples from all these cells and then process it within the stadium and get a lot of benefit. So those kinds of use cases exist, but not in a large scale. I haven't seen cell-free.
Okay, and one more question is that you talked about deep RX design. So is there any possibility to design deep TX also, like the transmitter and some FFT you are doing?
Yeah.
Maybe something else we can do using.
Yeah, we have a whole bunch of use cases. I didn't have time to talk about it. You can do beam management. Yeah, deep TX appears in two versions. One is the constellation design, and then the second one is waveform design, because you can say, okay, I want the best waveform in terms of minimizing the peak to average power ratio while achieving highest spectral efficiency, etc. So you can do waveform design, and then you can also do like the precoder design, right? Which tends to be mostly about channel prediction. So you get channel feedback, and then you try to predict forward because you're using the precoder a bit later, or the channel knowledge a bit later. So all of these things are being done, yes.
Thank you.
There is one more online question. So I understand that 6G aims to reduce explicit feedback overhead. How does the transmitter learns or predicts the downlink SNR for the rate selection? Is AI ML based channel prediction done by the transmitter for the rate selection in 6G?
Okay, I think this is a very good question. How to do MCS adaptation when we are doing these sort of deep RX type receivers, right? Yeah, I think one of the outputs of this should also be like, what is the equivalent of the SINR that's being observed, right? So of course, if you can demodulate the bits, you can easily calculate an SINR from that. Basically, you have the raw input and the demodulated bits. So by just comparing them, you can get an estimate of how noisy the received signal is. And from that, you can predict what the SINR is and then do the MCS selection that way.
Yeah, so in one of your earlier slides on talking about the spectrum, you mentioned about the upper mid-band frequencies coming up for 6G.
Yeah.
My question is, what are some of the pros and cons of that band compared to the sub-6 and the millimeter wave, and why was it also not thought in 5G itself?
Right. So I think in 5G, we thought that millimeter wave could be something that's easier to get, right? So it's a combination of what we think is available or will become easily available, and what we can achieve with that spectrum, right? So in the 5G days, people thought that we can actually deploy networks with millimeter wave, and it's better than the mid-band because we have much more bandwidth. But then we've learned that the coverage is a huge problem. Now that's the reason to look again at the lower frequency. With difficulty, can we acquire what spectrum, right? Earlier it was, okay, it's very easy to get the millimeter wave spectrum. Nobody's using it. Let's go deploy there. But now we are saying, okay, that doesn't work. So let's come back and see what is the best piece of spectrum that we need that can be made available. So it's a realization that higher frequencies don't work very well. So take another look at the lower frequency, see what you can get.
So have there been any challenges identified or yet to be identified in this band, or?
To acquire the spectrum, yeah, there's a lot of challenges. I mean, in the US, it's almost unlikely we'll get anything in the 7.4 to 8.4 type bands because of use of military in those bands. Similarly, in Europe, there's no hope of getting that spectrum. But in Europe, the 6 to 7 looks pretty promising. And in the US, this one big beautiful bill basically said 800 megahertz of new spectrum should be identified below 6 gigahertz by FCC. So different countries are taking different paths. And I had that one chart which is highly fragmented histograms there to show that each country is focusing on different bands for 6G.
Thanks.
Okay, thank you for your nice presentation. My question is on meta surfaces.
Yeah.
Given their envisioned functionalities, which ranges from creating virtual line of sights to beamforming and near field focusing, all those diverse, even on the air mixing, as a contendant to relays and also MIMO, can you elaborate on its future and the work that is being done at your company?
Okay, that's a good question, right? So as of now, we are mostly focusing on beamforming using the meta surface. Yes, people have also talked about stacked meta surfaces where you can have many of them and do signal processing using just analog signals. The RF signals can do signal processing. We also have some work on doing frequency selective filters using the surface. So the surfaces are designed so that you can already filter some of the out-of-band signals before it goes to the digital filtering. So that's another use case. Yeah, I mean, I think in the future we may look at more processing in the meta surface if it makes sense, but we haven't done that now.
I hope sir has answered all of your queries. In the interest of time, we'll conclude the session here. Thank you all for attending and have a great afternoon. We have arranged refreshments at Coffee Hut as well. Please feel free to continue our discussions. Thank you.
Thank you very much.